All right, everybody, we're going to talk about periodic trends today. This image here on page 59 is really the final piece that you really need to understand. The idea that from the periodic table, ionization energy is going to increase. So that means the energy to remove electrons increases from the bottom left to the top right. At the same time, the atomic radii get smaller. So these are the smallest elements. And the largest are on the bottom. And then the electronegativity also increases. So we can think about electronegativity increases, atomic radius decreases, and ionization energy increase, all in the same general trend. So let's go through those one at a time and talk about why that could possibly be the case. So I'm just going to scroll back up. Hopefully this isn't making you dizzy. So, factors affecting force on an electron. This is the idea that we wanted to talk about. We want to think about the electron and the atom being sort of thinking about the Coulomb law that is affecting an electron. So I did a little bit of work here. I'm going to just kind of copy this and we're going to talk about this image I made here. So let's just duplicate that. Okay. So if we think about three elements here, this is this one, we have a fluorine, we've got a chlorine over here, and we have our helium on the left. In the case of the helium, if we think about the electron configuration, we have two protons on the center of the nucleus, and then at the first shell, right, at the n equals 1 shell, we have 2 electrons because helium has the 1s2 configuration. We know that Coulomb's law is the force between two charges, and that force is equal to some constant times q over r squared. So r squared is distance, and we can think that n is proportional to r. So whatever the n value is, that's proportional to r. And then q is the charge, right? So this is going to be the charge of electron. And then this will be the charge of the nucleus. And that's going to play in a little bit into what's going to happen. Charge of nucleus. So for the case of helium, all of the electrons are equally attracted to the center nucleus. Now, when you move to a larger element like fluorine, so maybe I'm just gonna choose to move this chlorine out of the way so I can talk about fluorine. So when we talk about fluorine here, these first two electrons, the two electrons in this first shell, they are attracted to the nucleus, just like the ones in the helium are. But if we want to think about sort of the force on these electrons now, their force is proportional to 7 protons, the 7 protons of the center, times this 1 electron, divided by the radius. And let's just, let's use 1, because the radius here is n equals 1, which is proportional to r. It's not an exact proportionality. Don't ever think that, the radiuses are like 1, 2, 3, 4 angstroms or anything. No. It's just that we can kind of use it as a placeholder for it. So we got some sort of value of r. And so we can think that this is actually a really strong force then. These electrons in the center are actually really attracted. And in this case, these electrons, are very strongly, we can kind of think that there's this very strong force attracting them inwards. So they'll actually notice when they do the calculations that these inner shell electrons are actually very small. They're smaller than you might expect. As the nucleus gets more protons, the attraction of those core electrons is higher. Now, if we switch out and we start talking about this electron here, I'm not sure if I want to talk about this one because it's going to get in the way. So actually, let's just move over a little bit. So what am I talking about with this little arrow that I wrote? Attracted by. So if we think about this electron, right? This electron just sees like a big old gas cloud here, right? It just sees the force it sees all of this as one thing. It doesn't see it as a separate nucleus and a separate electron cloud. All this electron sees in the second shell, in this n equals 2 shell, all it sees is looking inwards an attraction to this general center charge thing. But the central charge here is the sum of any electrons and protons that are smaller than that electron. So for this electron, we get a force that's not 7 protons. It is instead a force that is proportional to the difference, the 7 protons minus the 2 electrons, to give us a total of a proportional charge of 5. So it's like it's attracted to 5 positive charges, and times the 1 electron. So divided by, and now the n is increased, so it's like sort of, 2 squared or something. So not only the distance farther, but the distance has increased, right? I'm just going to type it because I find that my writing is getting pretty... Give me a box here. So not only is the distance increased, n equals 2 now, but for these electrons, they see the cumulative charge. So they experience, let's say experience, the cumulative charge of, so the force of attraction is only 5 positive. 5 positive. And we could take this and so that's what we call shielding. This is what we call the shielding effect. So the farther the electrons are out, and the more inner electrons there are between them, the more the shielding is. So we can see I did the same model for chlorine down here. So here's our chlorine model. And you can see that the first electrons get the full force of the 17 protons. But then you have to take all of this into effect when you consider the second shell. So this is our n equals 1. For our n equals 2 protons, or 2 electrons, then those electrons are only experiencing an attraction to a 15 plus charge. And for n equals 3, they are only experiencing the attraction to the remaining 7 electrons. And each shell is increased in size, right? So that also means that there's a change. So you kind of think that these are attracted by this little orange arrow. That's not great. Let's try a different color, something I can see. So we've got an arrow here, but it really, I guess the arrow kind of stops at the edge of this charge ball here, maybe. And then the other ones, they're attracted all the way to the edge of this ball. And then these ones get to fully attract right to the core. Maybe something like that. Kind of works. Okay, so that's shielding. This is going to play really importantly into considering the atomic size. So and especially ion sizes. So the nuclear charge, the more protons there are in the nucleus, the greater there will be in a nuclear charge. The greater the nuclear charge, the more force there'll be on each electron in the atom. So this is a key point. These are the only three things that are really going to dictate the rest of these properties. The distance of the electron from the nucleus, right? Distance of the electron from the nucleus, according to Coulomb's law, the further two charges are from each other, the lower their force of attraction on each other, similar to the gravitational law. And then we have the shielding effect, which we just described. Okay. So the trends in atomic radii, the number one effect here is, the number one effect that makes things bigger is shells. So radii, so the first thing to consider is that radius increases with electron shell number, n. Okay, so the higher the n, if you're comparing two elements, always check these things. So if you're comparing two elements, the larger the shell, the bigger the element. So if you can figure out their if you can work out the electron configuration, the larger the shell, the more electrons. Well, the larger the shell number, the larger the n number, the bigger the element. The second feature is to consider the effect of shielding and the effect of the nuclear charge, the nuclear charge effect for elements the same size. When the shell number is the same, consider the effect of the nuclear charge on attracting electrons. Okay, so we're going to consider the shell number being the same and then the effect of the nuclear charge. So let's consider lithium, carbon, and fluorine. So these are three elements in the same row of the periodic table. And we know from their electron configurations we did in the previous section that they should look like something like this. 2s, 2, 2p2, and then the fluorine, which is the 1s2, 2p, 2s. Why am I want to fill in those p's first? 2s2, 2p5. So in this case, we're going to place an electron here, an electron here, electron here, an electron here, electron here, electron here. Those are our 1s2 electrons. Thinking about these 1s2 electrons, I initially drew them all the same size, but if we think about the attraction, we actually need to shrink them a little bit, right? We need to actually shrink them down just a little bit, and this one just a little bit more, so it actually will be quite shrunk comparatively, because these three have different amounts of force on these electrons. We have, if we want to draw a little arrow, we have a little arrow here, we have a little bit of a bigger, thicker arrow here, and then we have this massive arrow right here. This is a huge attraction. So we can think that the amount of attraction to that nucleus is getting larger. Okay, so let's do the same thing for our electrons. Here, let's just put one electron out here. It will have even less than the last time, than the arrow I just drew. So I'm just going to put a little tiny arrow, and it's only going to go to this next shell where this is the edge of the charge. So that's the combined charge of the center. So it actually only is really feeling a +1 charge. I think I should make my arrowhead a little bit smaller. Okay, so a little bit smaller arrow, like that. On the next one, we have carbon electrons. Now notice that we're treating each electron individually because they are all equal in this case. We know a little bit more than I'm letting on. We know that these are s electrons and p electrons. So there is probably a difference in terms of energy and the amount of attraction. In fact, we could probably even start to think that probably in reality, if we had to ever make a connection to reality, there's probably a difference between the s and p electrons and how much they're attracted to the center. But we don't really know anything about that here, or we don't really have the tools to be able to talk about that at this moment. So these electrons will be receiving a little bit of attraction, not quite as much as the other ones. So maybe I have to draw that again. But these ones are going to now be attracted to the center core here. So this force, if we want to think, this force is, proportional to the 6 protons. This force is proportional to, 6 protons over n equals 1 squared. And then this electron here is getting only 4 protons, but divided by n equals 2 squared for our radius. And then we're going to put another electron here and an electron here. This is fluorine, so we still have 7 electrons to go. This is why I told you not to get rid of those Bohr models. They still matter. So with this one, it's actually got a pretty significant attraction because this electron is still attracted to a force proportional to 7 protons over the n equals 2 distance. So that's a lot. That's quite a bit more. We should probably fill in this one. Over here we have a force that is the force of attraction is proportional to only 1 proton because the first 2 protons are shielded. N equals 2. So when we consider the electron shell of this outer electron shell, like this, we actually have to think that this one is a little bit shrunken. How do I get this shrink? Doesn't want to shrink. Oh, there it goes. Oh, so a little bit of a shrink on that one because it is attracted to a little bit more energy, a little bit more than the previous. And then this fluorine is actually going to receive quite a bit of shrinking because there are 7 protons to be attracted to. So it's actually going to shrink quite a bit. And so for the atomic radius, the radius of a uncharged ion here, we are going to have an atomic radius that's decreasing. Right? So atomic radius decreasing. Now, of course, the atomic radius will increase if we add shells. That always will work to add shells, and it will increase in size. But the atomic radius will decrease if you have the same size shell. So all of these are n equals 2, right? All of these are dealing with the n equals 2 shell electrons, except that we have more and more protons on the inside, so the shell is being compressed closer and closer to the nucleus from the force difference. So when we go across the table, so if we think about our table like this, we have an effect where the size decreases. I'm going to get in here. Size decrease with nuclear charge. And then size increase with n. So we got an increase with n down and a decrease with nuclear charge across. This makes the smallest element up in the corner here. This will be the smallest. and this will be the largest. Okay, that's atomic size explained in full. You can see another version of this that we did in class on the right here, doing the exact same little bit of math play here. And so, as you move down a group, a new energy level is added, and so that increases the size. The addition of new energy levels increases the amount of shielding on the outmost electrons, resulting in lower effective nuclear force. As you move across to the right, you get the amount of shielding occurring on each atom remains constant, so the size of the atom decreases. The addition of the new energy level increases the amount of shielding on the outermost, so you produce a larger atomic radius. So that is how shielding is related to atomic radii. And here's another example of that. Okay, so the other one that's more tricky to think about is the ionic radii. So in an ionic radius, you are doing one of two things. If you have a positive charge, you're removing electrons. You remove an electron, and you're typically going to be removing an entire shell. So notice that with lithium plus, we went from 1s2 to s1. We've changed to 1s2. So now we have only 2 electrons being attracted by a force of 3 protons. That is quite a bit of force. So this little inner core is a really tight little tiny inner core. When we add an electron, we are sort of dividing up that force a little bit, and we are increasing the number of electrons, and the electrons the electrons end up repulsing on each other a little bit. Or the electrons can't be compressed as much because there's a higher chance that they'll interfere with each other. Pauling exclusion tells us that 2 electrons can't have the same quantum number, so we end up getting some problems. So if the charge is going positive, so in ionic radii, positive charge equals smaller radius than neutral atom. Negative charge equals larger radius atom. Electron shells are being removed. A negative charge is a larger radius because electrons are added, which push, which repel each other and increase radius. So you have less force, or there's less force to go around. That's another way of looking at it. Excuse that. It's not in a good spot that you can read it very easily, but that's the best we're going to do. Okay, so in ionic radii, if you remove electrons, then the elements get smaller. So for example, here we have lithium positive. It's only got a size of 90 compared to the original 134. And beryllium, and meanwhile oxygen was originally 73 angstroms, and now it is 126 when it's full. So, some good question types that we might see is, what's bigger? Let's try arrange from largest to smallest. And let's say, let's go strontium 2+. I really should have brought a periodic table here. Just one second. That's for my bio class. Periodic table of elements. Okay, let me think about this. Okay, so if we had strontium 2+, krypton, and maybe some rubidium. Let's just put that here. So if you had strontium, potassium, strontium, krypton, let's put in like selenium 2 minus, and boron minus, or bromine minus, and let's put in a rubidium somewhere, rubidium plus, and we had to organize those from smallest to largest. We would be looking for the most positive, smallest. We would first look and see. We would look for shells. So step one, consider number of electrons, and largest n. So in this case, all of these elements have the same number of electron. So in our case, we have all same number of E. So they all have the same number of E. And then number two, we're going to consider charge of ion. Larger charge equals smaller. So we would think that the strontium has the 2+ charge, so it's the largest. Then the potassium is, why do I always think potassium? Rubidium is a little bit smaller. It only has +1. And then we would think the krypton is the middle. And then the bromine has a -1. And the selenium is the largest. So smallest to largest. And so what we have here is I'm going to pull up that table again. Where did it go now? Okay. There it is. Okay. So we have strontium that has 38 electrons. So strontium here has 38 electrons, and it has electrons and 38 protons. But because it's +2, it only has 36 electrons. Then you've got rubidium, which has 36 electrons. All of these have 36 electrons, but only 37 protons. Here we have 36, 36, and then 35, 36, 35, and 36, 34. So in each of these examples, the amount of proton to pull the atom to make it small is decreased. So this one is the smallest because it has the most nuclear force, nuclear attraction. This one has the least. Okay, and the last thing to talk about is the ionization energy. This is the energy required to remove an electron. So so electrons can be removed one at a time. Every time you go to remove an electron, you're removing it from its highest energy position first, or from its outside, from the outside edge first. So usually from the highest n value first, and then keep going down. So if we looked at this example here, here's lithium. The highest energy electron would be the one in the 2s orbital. And notice that it's high energy, so the energy required to remove it, which we can think about as the energy of a free electron, one that has nearly infinite kinetic energy, is going to be only a little bit to jump. And then to pull out the electrons that are way down here, you're going to have a little bit of a higher jump. And then the last electron will be very difficult because the amount of force of attraction is actually going to increase, since the electron is now being attracted by the protons in the center. So the energy of these energy levels is actually from our old friend, the Coulomb attraction. So as you remove one electron, every electron makes it higher. So this may create some cool patterns that you can actually identify elements by their patterns. So here is a sodium pattern. So you can see that the very first electron is easy to remove because it's in the 3s orbital. And then all of the other electrons, they increase at a steady rate because they're all in the same shell, and each electron from that shell gets harder and harder to remove. The first two electrons in magnesium are easy. They're again in the 3s orbital, but the remaining electrons, which are all 2p orbital electrons, are harder to remove. And you might actually even notice that the jump right here, there's a little bit of a bigger jump, and that's because this is the last electron that you're removing from the down state, and then you're now entering a zone where, in this case, you've got all 3 electrons in the same direction, and they like to be all in the same direction. Half filled is always more stable, so the next jump is actually a little higher to get to that next stage. Anyways, that's a pro advanced move there. Aluminum, you also get a similar pattern. You get the first 3 electrons are free, and then the next ones are much, much harder. And these are huge jumps, right? We're talking about 10-fold jump in energy. So that's quite a bit. So you won't really find any examples of aluminum 4+ anywhere, as we really only treat the first 3 electrons as actually being active and able to move. So stare at these charts as much as you like, but what we want to realize is that for the first ionization energy, as you move across a group, so this is across sodium, magnesium, aluminum, silicon, you can see that that first ionization energy increases. We can think about this again. This is because of that increasing effective nuclear charge. So shielding is the same. Shielding is the same across a period. So the nuclear attraction, so the attraction to the nucleus increases with atomic number, increasing this barrier, increasing the ionization energy. So this is like the ionization energy can be thought of the energy required to overcome the attraction to the nucleus. So the ionization energy therefore is going to decrease down the group and is going to increase across the period. And that's what we're showing right over here. Here's another example. You can look at, looking at hydrogen, lithium, sodium, and potassium. That's all down a group. You can see that that first ionization energy really decreases in power. Even across the, even if you go to the noble gases, you can see that the decrease is also there. So as the elements get bigger, the ionization energy decreases. This is what allows something like xenon to actually have some chemical reactivity. You can see that all of the noble gases are the highest in their group. This is why they're all placed together. They have the highest ionization energy, not mercury, of course. And so that's what makes them interesting and makes them worthy of being in their own group together, is their very high ionization energy. All right, and we're back to our summary. So atomic radius trend is opposite to ionization energy. Small radius, large ionization. Because the smaller the radius, the harder to remove the electrons. The greater the nuclear attraction from that small r. Electronegativity follows the same trend as the ionization energy. The higher the ionization energy, the greater the atom's ability to attract electrons in a bond. Also, smaller the smaller the radius, the stronger the atom can attract electrons to the bond. And this can actually be thought of again as a nuclear attraction because smaller atoms will allows the electron to get closer to the nucleus, increasing increasing the Coulomb force and the nucleus. Did I spell Coulomb wrong again? Coulomb. Well, good enough. Anyways, hope that helped.